So it's a great pleasure to have Geoff Stanley here. So please, Geoff.
Got it. Okay. Thanks, Georg. And thanks everyone for coming at these weird times, either morning or midnight, depending on where you are. So I'll tell you about some recent work that we've done on neutral surfaces in the ocean. If you don't know what neutral surfaces are, they're essentially like isopycnals, potential density surfaces, or if you're an atmospheric physicist, they're like isentropic surfaces, but better. And we'll explain what that means. So most of we'll focus on this topology work, which is stuff I did during my PhD at Oxford. And then later on, I moved to the University of New South Wales to work with Trevor and Paul Barker, and that we'll discuss the optimization work there. So what is a neutral surface? Well, the classic example of that is a potential density surface. So here I'm showing you the depth of a sigma-2 surface. So this is potential density referenced to 2000 decibars. So it says I have a fluid parcel of some salinity and temperature, and I'm going to just evaluate its in situ density if I bring it down or bring it up, whichever way you go, to get to 2000 decibars. So this is the depth of that surface. And you can see in the low latitudes, that surface is quite deep. It's around 2000 meters deep, say, for this particular surface. But then as you move towards the poles, the whole water column tends to get colder and denser. And so that surface will move upwards through the water column, eventually outcropping in the high latitudes. But you might wonder, well, Geoff, you said sigma-2 here, that's 2000 decibars is a choice, it's kind of an arbitrary choice of reference pressure. What if I used a different reference pressure? If you do that, you get a different surface. So you'd wonder, well, what should I do? Which surface should I use? So these are all examples of approximately neutral surfaces. And here I'm showing you now the depth difference between that last one, sigma-2, and a very accurate one that we'll discuss in detail called an omega surface. So it's a different class of approximately neutral surface that's actually a lot more neutral, close to neutral. So I made the surfaces have the same depth at a point in the equatorial Pacific here, but then elsewhere they'll diverge by quite a lot, say up to 200 meters or so. So if you were to plot some quantity or do your analysis on one of these surfaces, you would get quite different answers depending on which surface you use. So for example, if you're plotting potential vorticity, you might find it's more or less homogenized on one of those surfaces than the other. So the reason we really care about this stuff is because the ocean, you can think of it as kind of like a stack of Dutch pancakes, where you then pour some maple syrup over the top, and it'll very quickly run off the sides of those pancakes, and it'll very slowly diffuse down through the pancakes. So that's analogous to in the ocean. You have a very strong amount of stirring or mixing along the neutral directions. We call this isopycnal or epineutral. When you're talking about along a neutral surface, it's epineutral diffusion. And you have a very, very weak, like 100 million times weaker diffusion across those neutral directions. So that's a dianeutral diffusivity. Now, one application of this is to say you're doing layered ocean modeling. So you have ocean model with layered coordinates. This would also be applicable to doing inverse studies, for example, in the ocean. But let's say you're using potential density as your surfaces, and you come along with a prescribed isopycnal diffusivity along the potential density surface that's very strong, and a very weak across diapycnal diffusivity. Well, the very strong along potential density surface diffusivity acts to have a component that's actually across the neutral direction. So what this does is it creates a fictitious or a spurious dianeutral diffusivity, dF, and we can quantify that. It's essentially the along surface diffusivity times the square of the slope difference between the true neutral direction, so the slope of the neutral direction, minus the slope of your surface. So you want those two slopes to be very, very close because of this fact that there's 100 million times difference here. So you want this fictitious dianeutral diffusivity to be less than the canonical background diffusivity in the ocean, which is very small, 10 to the minus 5. So just to clarify then, again, like more carefully, what are we talking about here? What is density? When I say density, I mean the in situ density. That's how much stuff, how much mass there is per meter cubed. And it's a function, so this R is the equation of state. It's a function of the salinity, the heat, or we could call that the potential or conservative temperature, and the pressure. So if we take the gradient of this to figure out how density changes in space, we just use the chain rule, and we have terms like this: rho sub f, that's essentially the Halline contraction coefficient. So it's the partial derivative of the equation of state with respect to salinity times the gradient of salinity, and so on. This rho sub p will come up a lot in this talk. That's the compressibility, essentially. So now suppose that, I've saved that equation up here at the top. Now suppose you've got a really boring situation here. You've got some water of density rho naught, and you've got a bit of water inside there of density rho naught. And let's suppose you put a biodegradable plastic bag around that blue fluid parcel, and then you move it, displace it by this vector dr to a nearby water column. Well, because we put it inside this bag, it's insulating, so its temperature and its salinity remain constant. So its new density is just the original one, rho naught, plus the reason, plus the contribution of pressure changes. So the fact that pressure has changed and the bag is compressed or not. Whereas the environment has now got a density of rho naught plus the full density gradient in that direction. So that includes the salinity and temperature changes. So the density difference now between the blue and the orange parcels in the new location is just given by this equation n dot dr, where n is we call it the dianeutral vector, and it's the contribution to the density change that is purely due to the salinity and temperature, so not the pressure. So then if we want to, we can align this displacement vector dr to be orthogonal to the vector n. So then n dot dr is 0, and what will happen is that the blue parcel will be the same density as the orange parcel at this new environment. So it'll be neutrally buoyant, it won't have any recourse to move up or down, and everything will be nice and boring, which is what we want. So that would be what we call a neutral trajectory. It's everywhere perpendicular to this vector n. And then that vector n, or sorry, that vector dr, it was in one direction. It could be in a whole a range of directions, and that would define a neutral tangent plane. So at every point, you've got this vector n, and that's well defined everywhere. And then there's the set of displacement vectors from that location where you started that satisfy n dot dr, and that defines a plane. Then a neutral surface, building on that further, is a two-dimensional surface that is everywhere tangent to this neutral tangent plane. So this is a picture of a schematic of a neutral surface, and everywhere you've got this dianeutral vector n, and your surface is everywhere orthogonal to that. Okay. So I'm going to use this sort of notation here with an under tilde. So another way of defining a neutral surface here is one that satisfies this equation here. If I say I've got this neutral surface and have some property like P or salinity on it, the under tilde means I'm just going to evaluate the 3D salinity field, say, or the 3D pressure field on my surface, and then I'll even just do one more step and I'll project it onto the sphere so that you don't have to worry when you see this sort of grad P under tilde. There's nothing funny going on in those gradients. It's just like a gradient of a normal spherical field. So yeah, on a neutral surface, we have this one definition in terms of the salinity and temperature gradients counterbalancing in terms of their contribution to density. If you remember, we had that formula for grad rho. And so I could plug that in and instead turn this equation into this one, where we have a neutral surface is one on which the in situ density changes only due to pressure, compressibility effects. Okay. So let's come back to this picture now that we had before and make it a little smaller. And imagine, we start at this point, we do a neutral trajectory to here, to the next water column, and then let's say we mix with our surroundings. So now we take on the salinity and temperature values of the environment, and then we do another neutral trajectory here, and then mix again, and continue on in this fashion. That gives you a neutral trajectory. The weird thing is that if you come back to your original latitude and longitude position, you'll find that you're actually some point higher or lower perhaps than where you started. So we call that a neutral helix. It's like a screw where the threads go up helically. So you can understand this actually fairly easily. It's with an analogy to currency exchange. So in this analogy, rho, the density, is like wealth. So it's like how much stuff you have. And then salinity and temperature are like different currencies. So they could be like dollars and pounds. So imagine you start off with a great one-to-one exchange rate for simplicity, and you have $100 to 100 pounds. And then let's say you trade in your dollars to get 200 pounds. And then later on, some time later, the exchange rate changes, and now it's a 1-to-2 exchange rate. So you can trade in 100 pounds back in for $200. And so what you've done is you made a profit, which is like probably pretty unrealistic in the world of currency trading. But yeah, maybe you lost money either way. So in this analogy, rho s and rho theta, with the ratio, is essentially the exchange rate, and time is like pressure. So as time changes, the exchange rate can change. And the point in the ocean is that as pressure changes, these haline and thermal expansion coefficients change with pressure, and they change differently. So the way I remember that is this kind of nifty, interesting fact that if you look at Antarctic bottom water, compare that to North Atlantic deep water, normally we think of Antarctic bottom water as denser than North Atlantic deep water. It lies below it in the ocean floor, and North Atlantic deep water is less dense and lies above it. But that's only true if you evaluate their densities at some deep pressure, like say here, 4,000 decibars. But if you compare their densities at the surface, Antarctic bottom water is colder and fresher than warm and salty North Atlantic deep water. And it turns out at the surface, the North Atlantic deep water is actually denser than Antarctic bottom water. So this pitch that we had here, this is pretty unlivable. We really don't want to deal with discontinuities in our surfaces. So what we have to do then is use approximately neutral surfaces. So like the black line here, this is a continuous surface. The downside is that it's only ever approximately parallel to the true neutral directions. Okay, so the goal then is to come up with good approximately neutral surfaces. And there's been a lot over the years. So we've talked about the classic one already of potential density, just the density of your fluid parcel evaluated at a certain reference pressure. The other classic one is specific volume anomaly, which is the density minus a density of a certain reference fluid parcel with a given salinity and temperature at your local pressure. And actually, I feel like this one, specific volume anomaly, doesn't get used enough. It's quite great. Like in terms of accuracy, in terms of neutrality, it's similar to potential density. So there's no downside there if your alternative is potential density. But the nice thing about it is that it has a exact geostrophic stream function and an Ertel potential vorticity. So it's quite useful in terms of these oceanographic properties. Okay, so then there's some other ones, patch potential density, which was an old classic one where you try to use different potential densities with different reference pressures and you try to patch them together. The downside of that, though it can be more neutral than using one of these everywhere, the downside is that you get discontinuities. So for that reason, I'm not a huge fan of anything with discontinuities. Then another famous one, neutral density, from Jackson and McDougall in 1997. That's this gamma n, which is a function of salinity, temperature, pressure, as well as the spatial coordinates x and y, and a climatology from Levitas. So you might wonder, well, why is it a function of x and y? That's kind of weird, like latitude and longitude. And we'll have hopefully a better understanding of that by the end of the talk. But that is fundamental to neutral surfaces, that they are geographically dependent. So then there's two more here, orthobaric density and thermodynamic neutral density are new ones as well. And you can see orthobaric density depends on like specific volume anomaly, it depends on pressure and density. So it inherits all of those good oceanographic properties, whereas thermodynamic neutral density is a function really only of salinity and temperature. So it has that nice quasi-material property that potential density also has. Okay, but these are all three-dimensional density fields. So you could calculate these guys everywhere in the ocean and then take an isosurface, a surface of constant gamma n, for example, and you'd get a 2D surface. What we're going to talk about today are two-dimensional bespoke surfaces so they only exist at one depth. You can build them at all sorts of different, you can build a whole continuum of them if you want to, but at any time, you're just building one surface at a time. So these two that we'll focus on are omega surfaces, first made by Clucker in 2009, and then we updated them recently. So this uses matrix operations and optimization, and then the other one are topobaric surfaces, which use topology and graph theory in a kind of fun way. So, oh, I can find the chat. Okay. Okay, but if no questions, I'll carry on. Okay. There we go. So we finished a bit of a review and motivation for why we care about this stuff. So we'll talk about omega surfaces, then we'll get into the topology bit and topobaric surfaces, which use the topology. And then if we have any time left at the end, I'll talk about geostrophic stream functions. So omega surfaces. So what are we talking about? Okay, here the tilde is on top. Apologies, it's the same as having the tilde below. So an omega surface is one that tries to minimize this quantity epsilon. So if you remember, a neutral surface is one for which this quantity here is equal to 0. So what we'd like to do is minimize the error from 0 in this expression. And the way omega surfaces do that is they will start off with an initial surface. So it could be a potential density surface, for example. And then they'll solve this constrained minimization problem, where you first calculate epsilon on your initial surface, and then you're going to try to find this phi field that minimizes this quantity here. So it's an integral over the entire surface of the square of grad phi plus epsilon. And the idea here is that once you've got phi, we're going to use phi to update the depth of the surface. And we expect, or we predict, that on the new surface, this grad phi plus epsilon will be the epsilon error on the new surface. So we'd like to minimize the error on the updated surface. So we're going to try to minimize this grad phi plus epsilon. And of course, the gradient of phi is arbitrary up to a constant. So we're going to specify phi at some latitude and longitude to be 0. Okay, so we can discretize this. Grad phi turns into this matrix G, essentially, times this phi vector. So at every water column, say in this example, 1, 2, 3, 4, 5, 6, 7, we can ignore this stuff up here. We have 7 values for phi, and then the matrix G takes this gradient in the discrete space. So down here, I've just listed which water columns are adjacent to each other. For example, water column 1 is adjacent to water column 2. And that manifests in the first row of this matrix. You have a -1 and a 1 that multiply and give you phi 2 minus phi 1, right? Okay, so that's the gradient on a uniform grid. And that is supposed to equal negative epsilon evaluated between columns 1 and 2. So the thing about this matrix G here is that, like, in the asymptotic limit, as you get to a large domain, it's roughly twice as tall as it is wide. So it's an overdetermined matrix problem. And so we're going to want to solve the least square solution of it. The square is to give us this guy here, the square. And the original code from Clocker, McDougall, and Jacket solved this using the LSQR algorithm. Turns out we can do better. So we can take that constrained minimization problem and really, like, you just apply the calculus of variations in a pretty routine way. You just turn the crank and out pops a Poisson equation. So now we have a Laplacian of phi equals the negative divergence of epsilon with a boundary condition as well. So if we can discretize this one, and you get a discretized Laplacian operator, and on the right you have a discretized divergence operator applied to your epsilon vector. So yeah, the Laplacian, you might recognize in row 4 here of this Laplacian matrix, you have a 1, 1, minus 4, 1, 1. So that's like the standard stencil for a Laplacian on a uniform grid. The great thing here, the bonus, is that the Laplacian matrix is square, and it's symmetric, and it's full rank. Once we add the condition that phi is 0 at some particular point. So we can solve this more quickly using a Cholesky decomposition. I won't go into the linear algebra of that, but we'll see that that actually improves the computational complexity of the whole algorithm. Okay, so now that we've got phi, by solving this global linear problem, now what we need to do is use phi to update the surface. So the original code from Clocker, what they did is they took phi in each water column M, and they essentially divided that phi by the stratification, essentially. So sigma is the potential density reference to your local pressure, and then you could imagine that the sigma dp stratification could be very near to 0. So that could be a worry that's potentially unstable. So they had to add a damping factor, lambda here, and then they get so they've turned this phi, which is a potential density perturbation, by dividing by the stratification, you turn it into a pressure perturbation. And then you update the pressure according to that. You just move up by that amount. So essentially, what that does here, if you look at one water column where you've got pressure in the vertical and then potential density on the x-axis here, and you start at some position here, essentially what they've done is they've taken a linear approximation to the true profile of sigma with respect to pressure. And then they say, okay, well, we're supposed to move by this amount phi in potential density. So I'll just move by that amount and then figure out how much I have to move according to that in pressure space. So what we do is we solve this nonlinear equation in the bottom left here, which uses the whole information on the water column. And so we just figure out what is the pressure at which the potential density has changed by this amount phi. So it's a little bit more work to solve this nonlinear problem in each water column, but it's, it's very easy actually. And the great thing about that is that it is much more stable. So there's no fear of dividing by a small number. And it turns out that this reduces the number of iterations required by the entire algorithm to reduce quite a lot. So the original algorithm took something like 50 iterations typically to converge. This is blue, the original omega algorithm, whereas the new algorithm in red takes about 5 iterations. Okay, what am I showing you here? So this is an aquaplanet example data set that's 128 grid points wide and across. And the y-axis is the root mean square of the neutrality error. So you want to be low down on this graph to be accurate, to have a surface that's quite close to neutral. And then the x-axis is computation time. So you want to be towards the left down here to be fast. So I'm showing you a bunch of different surfaces here. And the top two here are sigma potential density and delta specific volume anomaly. So those aren't iterative algorithms. You just calculate them right away. So there's one point here, and they're very, very fast. And then the original omega code, as I said, this is actually measured in minutes here, so that's 2 minutes. Whereas the new omega code on this data set is a quarter second. And then also just for comparison, the topobaric, which we'll talk about in the second half, is in green here, is also very fast and a little bit less neutral. So we'll talk about that. Okay, but that was just one tiny little grid at 128 squared here. Now let's see what happens as you change the grid size on the x-axis here. And again, now the CPU time for each algorithm is on the y-axis in log space. So the classic algorithms, sigma and delta, these guys scale linearly with the number of water columns, n, as you'd expect, and they're very fast. So they're low down on this graph. Whereas the original omega code, it's just higher up, so it's a lot slower, and it scales, its slope is larger, so it scales more like n to the 1.6. The new code, however, so we call this omega plus, this scales more like n to the 1.2, and so that's the difference of using the LSQR solver versus the Cholesky solver. The topobaric code in green, it's also very fast, but it seems to scale a little worse with large grids, which is an interesting fact, actually. Okay, so now we're going to get into the topology. It's actually very simple in terms of the topology that we use, and I'll explain it all with pictures. So if you've never even heard the word topology, that's okay. You can still follow along. So to make theoretical progress, what we're going to do is we're going to assume that the helicity is 0. So if you remember, helicity was the thing that said when helicity is non-zero. Oh, maybe I didn't say this actually. May have cut that slide. There's this quantity called helicity, which determines the fact that those neutral trajectories that we had are helical and they don't come back to where they started. So the amount that they diverge from where they started, that's due to this thing called helicity h. But we're going to pretend like that's not a problem right now, assume helicity is 0, and we do have true neutral surfaces. So yeah, essentially I'm just saying we have a neutral surface, and this was one of the definitions we had for it. The gradient of density on the neutral surface is proportional by the compressibility factor to the gradient of pressure on the neutral surface. So here's an example neutral surface, let's say, in this toy ocean. And I've drawn some pressure contours here on the surface. That's the P equals 1 contour, P equals 2, and so on. Now, the gradient of pressure is orthogonal to the contours of constant pressure. And then we can apply this relationship that says that grad P is proportional to grad rho. So the gradients of rho and P are aligned, they're parallel. Okay, but then again, you play the same game, and the contours of density are orthogonal to the gradient of density. So now I can draw the contours of density on this plot as well. So you see now that the contours of pressure are the same set of points as the contours of density. And that means that there's a functional relationship here. So if you tell me, Geoff, I'm on the P equals 1 contour, what's my density? I can say, oh, your density is 2. Or if you say you're on the P equals 2 contour, then the density is 4. So yeah, it's a functional relationship, and we'll call that function the rho hat. Okay, so I've moved that example down to the bottom corner here, same numbers and everything, and now I'm just going to build a bigger picture here. So I've added some more contours here. The thing here now is that on this P equals 2 contour, in the bottom left, the density is actually 5, whereas on this one it was 4. So what that means is that this rho hat function is actually multi-valued. It's a function not just of pressure, but also of x and y. So this gets to that question that many people have wondered: why is neutral density a function of salinity, temperature, pressure, as well as x and y? Well, this is why. WHY. However, you don't actually need to know the whole x and y position that you're on. You just have to know what pressure contour you're on. So I just need to know I'm on this one on the left, if it's P equals 2, or this one on the right, P equals 2. And this is where the Reeb graph comes in. So the Reeb graph takes each contour of pressure, like this P equals 1 contour here, and it sends it to just a single point in the Reeb space. So that's that point, that contour, P equals 1. Same thing, P equals 2, that contour. And you could sweep up and down and look at all the P contours between a minimum here and this saddle point, and you'd sweep out this line in the Reeb space. And then you could do that in this region over here with the different contours, and you get a different line in the Reeb space, right? So this P equals 2 contour is different from the one in the blue region, so they give you different points in the Reeb space. And so what we're doing here is we're building a graph. So if you've never heard of a graph before, conceptually they're very simple. It's just a collection of nodes, so that's the black dots, and edges. And what's an edge? It's just a line between 2 nodes. Okay. So there's something special here. The leaf nodes, like little b and little a, these correspond to extrema, so maxes and mins of the pressure field. Whereas internal nodes, so the capital A here, corresponds to saddle points of the pressure field. And each edge of the graph is associated with a region in physical space. So the yellow region here is associated with a region where the rho hat function is single valued. Okay, so we could build up a bigger picture here, fill in the space here. And I've also included some islands here. So the islands do something interesting. Like along this P equals 6 contour, you have one value for the density rho. But on the other side of that island, you have a different value for density rho, potentially. So what that does is the island has created what we call a cycle in the Reeb graph. So a cycle in a graph is where you can walk around and get back to where you started without ever backtracking. It doesn't always happen though. This island up here has a closed P contour that surrounds it entirely. And so it turns out it doesn't produce a cycle in the graph. So you have to be wary of islands, which we'll come back to. Okay, just to recap then. So we have a neutral surface, hypothetically, on which the gradient of density is proportional to the gradient of pressure, and the contours, therefore, are aligned. And so there's this multi-valued relationship between density and pressure. And in these regions, colored regions here, which are edges of the Reeb graph, this multi-valued function rho hat is actually single valued. So here is just a schematic example of what that multi-valued function might look like. So below, shallower than this PA saddle pressure here, we have 2 branches of that function. So if you evaluate rho hat at some pressure less than PA, there's going to be 2 options in the blue or the yellow region. And importantly, this rho hat function, the branches of it have to meet continuously at the saddle pressures. Okay, and we'll talk more about why that is and cases where that's not true. Okay, so again, so we have a neutral surface which obeys this relationship between density and pressure, and it implies this multi-valued relationship. So if I take the gradient of this multi-valued relationship, I get grad rho on the left, and I get the derivative of my rho hat function times the gradient of pressure. Okay, so now if I'm going to combine equation 1 and 3 here by equating the left-hand sides, and if I do this at places where grad p is not 0, so away from the saddle points and the extrema, then I'll find that this d rho hat by dp, the derivative of rho hat, is just equal to the compressibility from up here. Okay, so that means that actually this rho hat, d rho hat by dp, this is also a multi-valued function of pressure. So we'll give it a new symbol. We'll call it pi hat. So pi hat of p gives you the compressibility at any p, and it's multi-valued. Okay, so pi hat is the derivative of rho hat, or we could turn that around and say that rho hat is the integral of pi hat. Okay, so if I want to evaluate rho hat at some pressure, I just take you get a constant of integration, and then you integrate the pi hat function. Okay, so we'll come back to this in a moment, but first we got to ask, well, what happens at the saddle pressures here? Because does pi hat exist at the saddle pressures, and how do the different branches of pi hat meet? So we've hung on to these equations here, and we're going to look at what happens. So another way to get the fact that we have a functional relationship for pi hat is to take this definition here, and instead we just cross-differentiate it, or we take its two-dimensional curl or its Jacobian kind of thing. So that kills the left-hand side with 0, and we get grad compressibility crossed with grad pressure, or essentially like the Jacobian of those two fields. And that is the same sort of thing. Like, it also says that the gradient of compressibility is parallel to the gradient of pressure. So that is another way to deduce that there's a multi-valued functional relationship between compressibility and pressure, at least wherever grad p is not equal to 0. Because if grad p is 0, you see, this equation is satisfied regardless of what value for grad compressibility there is. However, we're going to say for now, though, that pi hat must meet continuously. So these branches of pi hat have to meet continuously, just like for rho hat, because at any point at the saddle point here, we have a field of salinity and temperature and pressure in space. And so long as those fields are not discontinuous, as long as they're continuous, then the compressibility must be continuous. And so then the compressibility as a function of pressure must be continuous. Okay, so that's probably what would happen. However, you could imagine a little special case here where instead of having saddle pressure, we have a large region where grad p is 0. So this is a flat region. And there's a distinction now that I want to raise between this top equation. When grad p is 0 here, it means that grad rho is 0. So rho is constant in this flat region as well. But in the second equation here, when grad p is 0, the gradient of the compressibility can be whatever it wants. It could be very large. And so that means that the compressibility can actually change very rapidly around these saddle points. So that's a fundamental difference between these two types of equations. And I guess I'm just saying this in part because you'll find equations like this, like either of these in physics or many different fields. Like I'm curious to find them in more and more fields, maybe economics, who knows. And when you find an equation like this, you get this multi-valued relationship, and the read graph becomes the proper tool that you would want to use in order to study that multi-valued functional relationship. And since functional relationships are extremely powerful tools to simplify a problem, this read graph technology might prove very insightful for different problems in physics or other fields. And so if you see these equations again, but also remember then that there's this fundamental difference between these two types of equations that give rise to the functional relationship. Okay, so in this flat region, we have that salinity and temperature can vary so as to maintain a constant rho. As I said, grad rho is 0, so rho is constant here. But you can't also maintain this other condition that the compressibility is constant. So the compressibility could change as you move across this region, and that means that these branches of pi hat could meet discontinuously at the saddle points. And that will prove to be very useful later on. Okay, but let's come back to this equation here. So I said rho hat is an integral of pi hat, but I've written it just in terms of simple integral of pressure. And you're probably wondering, but you said pi hat and rho hat are functions of, they're multi-valued as well. So how does that come in? So it comes in by a path integration. So rho hat at some pressure here, say P, if we want to evaluate the density at this point here in the pink region, well, the density is some value there. And I could rewrite the density as a path integral starting from this white point here. So I've got the density there, and I just do a path integral of grad rho along that path. Now, if I use the neutral relationship, that's grad rho becomes compressibility times grad P, which I can then use the fact that pi hat of P is the compressibility, and then turn grad P dot dr into dP. So this is how you evaluate this integral of pi hat. It's actually via path integrals. Okay, if this still looks a little sketchy and confusing to you, well, let's make it very clear. That's what I had before up here. And so this path in physical space corresponds to a walk in the Reeb graph. So it tells you how you move through the edges of the Reeb graph. So this is how you do it. There's nothing funny going on here. These are simple integrals. So the density at some pressure in the pink region is you integrate the pi hat function in the pink region from its boundary at 10 up to the pressure you're interested in. And then you integrate through the green region as you go through there, and then you integrate through the blue region, the light green region, until you get back to your red region where you start, and you have a free constant of integration. Okay. So the thing is, there is one funny thing here, and that is that you could take a different path to get there. So you could go on the inside passage here, and if you're not lucky, you could get a different answer. So, well, you shouldn't get a different answer. The density here is just some value. It has to give you the same answer, or it should. In order for this formulation to work, this theory to work, you have to have that the integral of the pi hat functions around the island is 0. So you have to think about the cycles in the Reeb graph, and they have to integrate in terms of the pi hat function to be 0. Okay, so that's a condition that we're going to have to use. It turns out, though, in the ocean, that's not true. There's no reason that the ocean would have to oblige us in this way. So in general, that doesn't hold. And why not? Or what does that imply? Well, it implies that islands can actually contain some of this non-zero neutral helicity. So I said that helicity H was this quantity that means that you have this helical pitch to neutral trajectories. And in the open ocean, you can have helicity that's non-zero that creates this pitch in the open ocean. My point here is that you can hide helicity essentially inside islands, and that creates a pitch of a neutral surface around the island. So this is just a theoretical point to say that it's not enough to demand that helicity is 0 in the ocean in order to get a neutral surface. You also have to demand that there's no hidden helicity. Okay, but now let's go back to the reality. Corsica and Vancouver Island, yes, Maurice, good job. Okay, so in the real ocean, there is non-zero helicity, and we don't actually have surfaces that are perfectly neutral. So what can we do? Well, let's go back and say, we'll build an omega surface, so it's quite an accurate neutral surface. And I'm just plotting now for you the pressure on that surface. So the 1000 decibar pressure contour, for example, here, the point of this theory is to say that along this pressure contour, the density should be constant, but it can be a different density than exists along this 1000 pressure contour in the South Atlantic. So now I'm showing you the pressure from that last plot. I'm just doing a scatter plot of pressure versus density, or rather the density anomaly, so that we just start to pick out some patterns. If I didn't take this anomaly off, you just basically see a straight line. Okay, so that North Atlantic 1000 decibar region, that was this blue region. I'll show you this as well. These are the regions of the Reeb graph. So the blue region corresponds to all of this data in here. And lo and behold, it's quite an accurate functional relationship. There's a little bit of scatter, though. It's not a perfect line because of this non-zero helicity, because of the fact that our surface isn't perfectly neutral. But the point is, again, inside this region in the South Atlantic, you have a different functional relationship between pressure and density. So what we're going to try to do now with topobaric surfaces is we're going to try to build surfaces on which this holds exactly. Rho is exactly a function of pressure. So I'm going to try to collapse all of these scattered regions into perfect lines. So we're going to do that by defining this rho hat function as the integral of pi hat as we did. Now I'll just evaluate that on the surface. So I've dropped in an under tilde there and apply this relationship. So now I have rho is equal to the integral of pi hat. If I take the gradient of this equation, I get grad rho here, and you use the Leibniz integral rule. So you get the integrand evaluated at the upper limit of integration, and you get the gradient of the upper limit of integration. So now what I'm going to do is I'm going to say in each of my regions of the Reed graph, I'm going to try to empirically fit the compressibility to the pressure to come up with this pi hat function. And if I combine these equations, you can see if I plug in the compressibility here, you can see I'm going to pick up the neutral relationship approximately. So the better I can fit this compressibility to the pressure, the closer I will get to having a neutral surface. And sort of as I said before about the pi hat functions don't have to meet continuously at the branches, at the saddle points. The other way to think about that is that with non-zero helicity, we won't actually have this cross product being exactly zero. It'll be some small epsilon. And so you can see when you're near a saddle point, grad peak is near zero. And so you can satisfy this equation by having a very large grad compressibility. So this compressibility can change very rapidly around saddle pressures. And that means that pi hat can change. Essentially, we're going to allow it to meet discontinuously at the saddle pressures. Okay, so that's a very useful thing, because if you look at the Reed graph in, say, a 10th degree ocean model, there's a whole lot of regions. So in each of these regions, there's a functional relationship. With the omega problem before, what we did is we had this global matrix problem, and that's where the global information about the neutral surface problem was handled. In the topobaric problem, in the topology situation, what we do is we're going to handle all of the global information through the Reed graph. So once we built the Reed graph, then inside each region, we just have to fit the compressibility to the pressure to get our pi hat functions. And because of the fact that we're allowing the pi hat functions to be discontinuous at the pressure saddles, it's basically a decoupled problem in each region to do this fitting. Okay, so we do have to handle some regions together. If you go around an island, you have to integrate the pi hat functions to get zero. So there's a bit of a coupled problem there still, but it's not very bad. So the computational complexity is not so hard. So the method to actually do this, you start with a neutral surface P, you calculate the Reed graph, you then fit the compressibility to the compressibility, sorry, you fit the pi hat functions to the compressibility, you integrate, so that this, again, this is a simple integral, but really what you do is you start off at a point and then you walk through the Reed graph and you make sure you hit every single region. And the cycle constraint means that when you go around the cycle in either direction, you'll still get the same answer. So now we've got rho hat. So then what we do is we want to say in each water column, X, I'm just going to find the pressure at which the in situ density is the density that the rho hat function tells me it should be. So that's a nonlinear problem that you have to solve in each water column, sort of like with the omega code. And then you repeat and do that until you're converged. So just to look at how good this is doing, I showed you a measure in the first half of the talk in terms of epsilon neutrality errors. This is now just a bit of a different way of looking at it. Like if you think back to the pancake analogy, I told you about this spurious or fictitious dineutral diffusivity. And again, that was quantified by this along isopycnal diffusivity times the square of the slope error between the neutral tangent plane and your surface. So this is showing you the fictitious diffusivity on a sigma 2 potential density surface. And it's very low. This is a log plot. It's very accurate, very close to neutral in the Pacific where the reference pressure is near the actual pressure. But as the surface comes up towards the sea surface, you get towards shallower pressures, then these errors become very, very large. And in terms of a root mean square, it's 5 times 10 to the minus 3 meters squared per second, which is, uncomfortably larger than the canonical background dineutral diffusivity of 10 to the minus 5. So if you use this for a surface in a layered ocean model, you would not be able to have an ocean model that had a very small diffusivity of 10 to the minus 5. So that would be a loser, you would say. So instead, a winner would be something like the omega surface, which has a root mean square diffusivity spurious diffusivity of 10 to the minus 7. So that's comfortably lower than 10 to the minus 5. You could use it successfully and not worry about fictitious diffusivity. And likewise, the topobaric one is 7 times 10 to the minus 7 in terms of its spurious diffusivity. So again, it's passed that test. Okay, so I'll just quickly try to tell you one more bit of theory, and then I'll wrap up. So just in terms of geostrophic stream functions, this is the horizontal momentum equation, and we're going to focus on those two terms in the middle, Coriolis and the pressure gradient. Just in the horizontal, that defines the geostrophic velocity. So if I transform this gradient of pressure, which is gradient at constant depth, into a gradient along, a gradient of pressure along the surface, and a correction factor due to the fact that I'm no longer taking a gradient at constant depth. I'm now taking a gradient along a surface. So that's just a standard coordinate transform that also uses hydrostatic balance. Now the goal here is to take this expression, this is a vector field, and I want to write it as the gradient of some scalar field, psi. And that psi is the geostrophic stream function. So it's not guaranteed you can do that, right? Because this this nu here, which is 1 over the density, is sitting outside this gradient, and we'll treat G as constant. G is gravity. Okay, so Trevor McDougall in 1989 proved that this stream function psi does exist, at least locally, if the domain is simply connected, simply by taking the curl of this vector field and showing that it's 0. And that means that this vector field is irrotational, and you can write it as a gradient of something. So, okay, let's just check that. You take the curl with G being constant, that first term dies, and you have the gradient of specific volume times the cross with gradient of pressure. Now we're talking about a neutral surface, so this, I wrote this condition before with rhos, but now with nu for specific volume. This is like the compressibility again. So if I plug this in here, I get grad P cross grad P, which is obviously 0. So psi must exist. So that's what Trevor proved around the time of my birth, but he didn't have a closed form expression for what is psi. So let's get that. Well, the great thing is we have this functional relationship now. Nu is a function of pressure. So here it is. This is the exact geostrophic stream function. Psi is equal to gz. That was just handling the really easy term because G is constant, plus an integral of the nu hat function. And really, again, this would be calculated using these path or graph integrals like we had in the first bit of the talk. So now just check that it is exact. You take its gradient. Well, you get G grad Z. That's one of the terms we want. And then you do Leibniz. So you get the gradient of the upper limit of integration. And then you get the integrand evaluated at the upper limit of integration. Now you use the neutral relationship. The nu hat of P is just nu. And that's exactly what we want. Gives you the geostrophic velocity. So you can use this to build a geostrophic stream function on any approximately neutral surface. So I proved it was exact on a neutral surface, but you can use it on a approximately neutral surface as well. So this is just to show you the error in estimating the geostrophic velocity in meters per second based on one of a couple of different estimates of the velocity. So this is the true velocity, like the ageostrophic plus the geostrophic velocity. So it's quite large. On the other hand, this is the geostrophic velocity estimated using gradients that are just at constant depth. And that's different compared to how I've calculated the true geostrophic velocity for these other guys, which is using the expression that is grad P and grad Z along your surface. So this is, on the right, this is like a lower bound on just how accurate we could hope to be due to numerical discretization errors. Okay, so we have a bunch of different geostrophic velocities. The Zhang and Hogg one, the Cunningham, McDougall and Clocker. This is called orthobaric Montgomery, which is another new one I came up with, and the topobaric, which is essentially the exact geostrophic stream function applied to an approximately neutral surface. So the cross here is basically the root mean square error. So we're talking about a millimeter per second, which is all right, but maybe not good enough for what you want. But it could be even larger. It could be a centimeter per second, a millimeter per second. Well, the new one is an order of magnitude more accurate. So, and also I'd just say this other one I created, it doesn't use any topology. It's essentially like the Zhang and Hogg one, but generalized a little bit. So it's also more accurate. Details will be, of course, in the papers. But I'm running out of time, so I'll just try to wrap up here. So in terms of the theory of neutral surfaces, I showed you that this this definition that grad rho and grad p are parallel gives rise to a multi-valued functional relationship between rho and p. And you can use the regraph from topology to find out the regions in physical space, so along your surface, where that multi-valued relationship is single valued. And it tells you also how those regions nest into a larger global structure. Okay, I derived an expression for the exact geostrophic stream function on the neutral surface, and we found out that islands do funny things and complicate the topology. So you can get helices, neutral helices even when there's no helicity in the open ocean. Okay, in practice, I've given you two new codes or algorithms to calculate very accurate approximately neutral surfaces. So omega is the one that's closest to neutral because it's really doing an optimization problem, so you can't really beat it in terms of its neutrality. And it's now very, very fast to compute. The topobaric one is still very close to neutral. It's still very fast to compute. And the nice thing about it is it has a geostrophic stream function that's exact. That gives you an Ertel potential vorticity. And I would just say it's the topologically correct extension of orthobaric density, which I mentioned earlier as having these nice oceanographic properties like the stream function, the Ertel PV. In the past, so this is Roland Azuka who made orthobaric density, and he tried to extend it to have some geographic dependence, say by splitting the hemispheres and considering them just the southern and northern hemisphere separately. The problem, as ever, though, was that he ended up having discontinuities at the equator. And the whole point here is that we're using topology. Topology is the study of shapes. So we're using topology to figure out how to partition the ocean in such a way that you can have this geographic dependence while still avoiding having any discontinuities. So there is a way to cut the ocean up into different regions, but those regions are more complicated than just like boxes, latitude, longitude, depth boxes. Okay, there's a couple new stream functions as well that are more accurate. And the algorithms, they're robust due to the nonlinear update that we use in the vertical. So you can safely use them without dividing by zero. Two other things I didn't get time to talk about. They're expansive now. So there's a capacity for these algorithms to do wetting. So if the surface outcrops at the sea surface, say, but then at the next iteration, it wants to come back into the water column, these algorithms can now handle that. And there's also a density label, like kilograms per meter cubed. You could say my omega surface has got a Veronis density, we call it, of 1027.5 or whatever it is. And finally, these algorithms are already used, so they're on MATLAB, they're in MATLAB and Python now as well on GitHub. Currently, the Python one, well, currently both of them are just for rectangular grids, like lat long grids, but I'm working on that, so you can still use it, or so you can use it on more exotic things like cube spheres and so on soon. Okay, and with that, I will stop and happy to answer any questions.
Well, thank you very much, Geoff. That was a fantastic talk and very interesting and beautifully presented. Lots of stuff in there. I'm sure there are questions. Anyone? There's a question by Stephen Griffiths.
Great talk, Geoff. I know I've seen it before, but I wonder if you could remind me the significance of the under tilde. It gets to be quite an awkward notation, and I'm just wondering, do I really need it? What does it mean? Because you don't always use it. Sometimes you write a gradient without it, and sometimes you write it with it. And I just wondered if you can remind me what it is.
Sure. So the alternative notation is, I won't go back through the slides because there's like 100 of them. The alternative notation is grad with a subscript A of, say, the pressure. And that means I'm taking the gradient of my pressure field along my approximately neutral surface, A for approximate. There's really no difference there. They're both perfectly horizontal vector fields that you get as a result of that. This is a bit technical. The only difference is that the grad A of P, it gives you well, grad N of P, say, if you do it on a neutral surface, neutral tangent plane, it gives you the gradient at every depth. Whereas all I'm saying is when you do grad P with an under tilde, you've picked out a surface and you just get the gradient along that surface. So the under tilde, yeah. Well, I just want to say that it's a perfect spherical gradient. So you project it onto the sphere. And then you don't have to worry about like any sort of rotations after that. It's already on a sphere, so it's just a normal gradient.
Great, thanks.
Georg,
Yeah, there's a question from the chat by David Marshall. Thanks, Geoff. Are you saying that topobaric surfaces now have density labels?
Yes, I am saying that. It's a little bit, it's the first pass at calculating a density label, because what we do is we just go down one reference cast and we pick a density label at that, say the equatorial Pacific, you could say. And if you did the same algorithm at a different cast, say in the Atlantic, you would get a slightly different label. And that's a problem that we'll have to sort out eventually, but for now, it's a good working solution to have a label.
Trevor, you had a question.
Yeah, back on Steve Griffith's question. I mean, Geoff's under tilde is the same as what we've been using, this del sub n or del sub a.
Yeah.
Geoff, I wondered if you might give us a little pearl of wisdom about the other deficiency of an approximate neutral surface, which is not only lateral diffusion along the wrong direction, but advection through the surface because of assuming that things are going on in that surface as opposed to the tangent plane.
Yeah, great question. So you could calculate if you have a horizontal velocity u, you could calculate u dotted with the slope error between your surface and the neutral direction. And that gives you a vertical velocity, which is actually saying if your horizontal flow is along your surface, well, it's actually acting a bit across the neutral direction because they're not aligned. So that creates a vertical advection through the neutral surface or the neutral tangent plane. And we would probably also want to minimize that. So that's a subject of future research also from our PhD student, Aaron Lang. And just one thing to say about that is that the topobaric surfaces potentially have a better capacity to handle that than the omega surfaces, because topobaric surfaces, I said, it's a function of rho and p. You could also reformulate them to be a function of s and theta. And that means then that essentially because the flow is going to generally be along contours of constant s and theta, that turns out to mean that this u dotted with the slope error will be a lot smaller. But that's the quickest answer I can give.
Gary, you had a question.
Yes, I've got a couple of probably silly questions. So toward the beginning, you had an optimization problem to find these approximate neutral surfaces. And as far as I understood it, you specified the error epsilon. So that was, you're not trying to minimize the error, you really specified it. And I was wondering what's the motivation behind that? Why do you fix a particular error that you want to manufacture a surface for?
So what we're trying to do is minimize that error epsilon. Like we're trying to get it as close to zero everywhere as possible.
Okay, but that's not how the problem was written. You're minimizing over phi and the epsilon was fixed.
Yes, so that's true. So the idea was that we're going to find the phi field that minimizes that quantity grad phi plus epsilon. And the idea is that we're going to use phi to update the surface. So so I didn't show this, but there's some math you can do that predicts that when you update the surface according to phi, the new error epsilon will be that quantity grad phi plus epsilon. So what we're trying to do is we have a surface and then we're trying to minimize the error on the next surface that we will get.
Okay, so it's an iterative procedure where you're solving iteratively optimization problems somehow.
That's right.
Okay.
Yeah.
And my second question was about, I don't know where it was, 3/4 of the way through, you had an algorithm to make a single valued relationship between the pressure and the density. It was like a 7-step algorithm or so, and I didn't follow how passing through that ensured that you had this single valuedness. Could you elaborate a bit on how that's forced? Yeah.
So we use the Reed graph to pick out these different regions within which it should be single valued. So I fit the compressibility, that pi hat function, to like compressibility to pressure to get this pi hat. And then
That's locally, right? Locally on each.
locally within each region, yeah. So I don't have to worry about discontinuities between adjacent regions for the pi hat function. So yeah, I kind of brushed over this, but what you do is you then do a walk through the read graph. So you start off in one region and you integrate the pi hat function to get to the boundary of that region. And then you hit a saddle point. So then you have a couple other regions you could go into, and you integrate pi hat again in both of those regions. So then you get rho hat in those regions, and you just keep on going through the whole ocean like this. As you move through the read graph, you're moving through regions in physical space. And the nice thing, maybe I didn't emphasize this, the nice thing is that because even though pi hat is discontinuous at the saddle pressures, because we're integrating over a discontinuity. So our rho hat density function will be continuous at those pressure saddles.
Okay, sounds nice. Okay, thank you.
Okay.
Stephen, please.
Yeah, thanks again. So Geoff, you and I chatted about this, but I want to get more elaborate discussion about the spurious diffusivity. You know,
Yes.
This goes back to Trevor.
Goes back to
and
Ronas.
the question,
Sorry.
yeah, fair enough. The question about running a layered model, say with sigma 0, sigma 2, what have you, and diagnosing a spurious diffusivity relative to the neutral direction, it's different than running a Z model, for example, with that spurious diffusivity. You're not mixing anything in the layered model. You're misaligning the transport in that model relative to a perfect neutral. So in some sense, the spurious mixing in the layered model is a phantom mixing. It's not to say that it's right, it's just different. And so I think it's important to keep that in mind when how we think about the spurious diffusivity. And maybe that's a question. Is it important? And maybe Trevor, or you can respond to that.
Yeah, so I guess what you're saying is it is different. If you have a Z-level model and you rotate your diffusion tensor to be along the neutral tangent plane, you'll eventually get a tracer, say anthropogenic carbon that you inject at the surface, will eventually make its way down everywhere, even to the bottom of the ocean. Whereas if you're running a layered model with potential density surfaces as the coordinates, and you turn off the diapycnal diffusivity, so it's just really like immiscible layers, you put in some anthropogenic tracer at the surface, well, only the layers that outcrop at the surface will take up that tracer. So it won't get to the bottom of the ocean. So it is qualitatively different. But I would say that the real ocean would take that tracer, inject it to the sea surface, and it would make its way all the way down to the seafloor, even if there was no dineutral diffusivity, because of these other aspects of the equation of state cabling and thermobaricity that cause mixing. So, I think Trevor wants to say something on this too.
Yeah, so I've had exactly that discussion with Bob Hallberg dating back 15 years, I think, and I've never agreed with it. If you think of tracing a fluid parcel for a short time, there's a certain temperature dot and salinity dot. Now, you can draw a line between those two epochs, and there'll be an angle on the TS diagram, and you can then claim that that's a good coordinate. That's where things are happening. And I'd suggest that using sigma naught or sigma 2 as a coordinate is one way of doing that. In other words, it's quite arbitrary. It's not oceanographic. It's not where the ocean cares to mix. And if you choose to analyze it like doing an inverse model with respect to whatever reference pressure or whatever line that we've just constructed on the TS diagram, you'll say, there's no dia surface mixing. And so therefore it's adiabatic and it's a good coordinate. No, it's just a random reference pressure or random angle you've chosen to have, which is unoceanographic. It's not a get out of jail card for free.
No, I wasn't claiming that. I was just trying to make the case that the diffusivity it acts differently. It's To diagnose a spurious diffusivity in a layered model and map it, say you have a diffusivity mapped, a spurious diffusivity mapped in a sigma 0 model, and then you put that into a Z model. You run the two models; they're going to be different, right?
Well, that's different because you've chosen to mix in two different versions of a non-neutral direction, either along sigma naught or along sigma 2 or along constant geopotential. They're all just random choices you've picked as a modeler to do lateral mixing in, and neither of them are ideal.
Yeah, I don't think I'm being articulate enough to have this discussion here. I'm not. Yeah, I'm not. I think we're cross talking. I see your
you
point.
called it a phantom diffusivity. Maybe I didn't quite get what you meant by the phantom there. But.
In the sense that you can run that layered model and preserve properties within those layers exactly, even though you're not preserving them within layers defined by neutral or omega surfaces or topographic surfaces. You're preserving the properties within the sigma 0 layers.
Yeah, so that's a great thing to do if you were modeling some fluid other than seawater.
Yeah, again, I'm not arguing that it's the right thing to do, Trevor. I'm just arguing that it's a distinction between that diffusivity that's being diagnosed and then it's applied to a Z model as a dipycnal diffusivity, not perfectly rotated diffusion in the Z model, but applying that as a dipycnal diffusivity.
Yeah, I think what you're saying is that if you run a layered model with, say, sigma 2, then I'd put it this way, that what you're doing is you're running a z-coordinate model. Equivalently, you're running a z-coordinate model, but rotating your diffusion tensor to the sigma 2 direction. And that's how I'd view it. And that's a good lens to view it from.
Yeah. And we've talked about doing that experiment.
Are there further questions? Well, then let's thank Geoff again for a great talk, and thank you very much.
Thank you all for coming.
Thanks, Geoff.
Hopefully it was partially understandable at least.